Now that we've seen the procedure, let's look at another non-dimensionalization example. This example comes from section 3.5 of the book, and the equation is a differential equation model for if we have a metal hoop that has a bead on it that can move freely, and the hoop is spun. And the equation is basically saying F, where equals ma. So ma is over on this side, mass times these two things combined to create our acceleration term. And then we have three different forces in the system. One is a drag or damping force for motion along the hoop. One is the force of gravity pulling the hoop towards the bottom. And the other is the centrifugal force getting generated by the rotation. So that's where this equation comes from. And we're going to non-dimensionalize. And then after we non-dimensionalize, we're going to look at under what condition the second derivative term is small. We haven't worked with second derivatives before, so it would be convenient if we were able to ignore this term. And after our non-dimensionalization process, we're going to see when we're able to ignore that term. To start, we identify the variables. They are theta and t. And then we identify the parameters. We have m, we have r, we have b, we have g, and we have omega.
Now I'll identify the dimensions. It's likely that I'm only going to need the dimensions of the variables to work on this problem, so let's take a look at those. The dimension of t is time. What about the dimension of theta? Well, actually, you might not think of it this way, but theta is a ratio of two lengths. The length of this arc to the length of this radius. And so because it's a ratio of two lengths, theta is actually dimensionless. Now I introduce my non-dimensionalizing constant t0. I'll choose the value of that later. And I introduce my non-dimensional variable. Theta is already non-dimensional, so I'll leave that alone. And then I introduce tau, which is my variable t, divided by the constant t0. And I reorganize that as t is equal to tau t0. Now, I'm ready to substitute this information back into the original equation and simplify. Writing the equation out, I have mr d squared theta d tau t0, the quantity squared, is equal to negative b d theta d tau t0 minus mg sine theta plus mr omega squared sine theta cosine theta. I'm going to divide through by mr and multiply through by t0 squared so that I have a non-dimensional quantity on this side of the equation. After dividing through by mr and multiplying through by t0 squared, this is the equation that I'm left with. I know that theta and tau are both dimensionless, so I know that this term is dimensionless. Since every single other term can be added to this term by dimensional homogeneity, every one of these terms is dimensionless. That means that I'm now ready to identify my dimensionless groups. By dimensionless group, I mean a group of parameters or constants that when put together has no dimension, but where each of the individual contributing parameters actually does have a dimension. I'm seeing three different dimensionless groups. B t0 over mr, g t0 squared over r, and omega squared t0 squared. I have one arbitrary constant that I have control over, that's t0, and so I get to choose t0 so that one of these groups disappears and becomes 1. I don't want to get rid of b t0 over mr. That's because I want to be able to compare the relative size of these two terms, and so I want this group to stick around. I'm actually going to choose to get rid of this group. To get rid of that group, I want it to be set equal to 1. For this to be 1, I need to set capital T0 to be 1 over omega. So now I've chosen my dimensional time scale that I'm using to non-dimensionalize the problem. I'm going to go ahead and substitute this T naught back into my other groups. Here are my new non-dimensional groups, the ones that are left after doing this substitution. The next step is to assign a new parameter to each of these non-dimensional combinations and rewrite our equation. I'll always choose a Greek letter for these new non-dimensional parameters, so I'm going to call this one beta because it had a b in the numerator, and I'm going to call this one gamma because it had a g in the numerator. Here's my final equation. I'm using primes instead of dots because these derivatives are with respect to tau rather than with respect to t. Theta double prime is equal to negative beta theta prime minus gamma sine theta plus sine theta cosine theta. The process of non-dimensionalization has given us an equation to analyze that looks a lot simpler than the original equation and that has many fewer parameters. In the case where theta double prime is quite small relative to beta theta prime and these other terms, then I might actually neglect this term. In that case, I would say acceleration was negligible, and I could treat this as the type of first-order system that we're familiar with.